Yeah, hello again. My name is Jens Dietrich. I'm Associate Professor at Victoria University of Wellington, New Zealand, and I want to talk about DALEQ, a tool we have developed to aid engineers working in software supply chain security, in particular for the Java platform. That is part 2. In part 1, I already talked about the basics of the DALEQ tool, and now I want to go a little bit more into the details of how DALEQ works underneath. So to recap, what the basic idea of DALEQ is, we basically run the analysis on 2 jar files. Those are the Java binaries built from the same sources. And in this particular case here, DALEQ has done an analysis, created a report, and it has compared package logback classic 1.3.11. The first version was built by the developer and released on Maven Central. The second version has been built independently by Oracle's built from source project and released in their private repository. So the really interesting case here is to compare the .class files. Those are the actual Java binaries which are produced by the Java compiler. And that's really the main purpose of DALEQ. And we can see, if we scroll down here, that we have a few class files. Again, remember that they have been compiled from the same sources to start with, but we actually get different bytecode. And the best way to see this is to use the second to last column here. And it doesn't really compare the bytecode directly, but it compares the disassemblies from the bytecode using the standard Java disassembler Java P. So we have a look here, and we can see that those 2 jar files actually use different bytecode instructions. So there's an invoke virtual invocation in one of the jar files, in one of the classes, and the other alternatively built version of the same class has a different bytecode instruction, invoke interface in this case. So DALEQ can still establish those 2 classes as being equivalent, and that really helps an engineer who has to assess whether non-equivalence could be related to compromised security. So how does DALEQ establish this? Let's first have a look at the homepage, and there's a drawing in there that basically describes this on a very high level. So let me just use this here. So the input is 2 Java classes, which means 2 .class files. So they usually come from Java source code, but they could also come from Kotlin or Scala bytecode, source code. So the first step is that DALEQ performs an extraction using the very popular ASM library. It's a very low-level bytecode analysis tool, and that faithfully extracts each bytecode instruction we find in the .class file and stores it in a record in a table, and each bytecode instruction has its own table. And that results in 2 relational databases, EDB1 and EDB2. So if you wondered, EDB stands for extensional database. That is Datalog lingo, basically. So then we build a second database, and we call them IDBs, intentional databases, in Datalog speech, by applying certain rules. And by default, those rules are basically just a one-to-one mapping. Nothing really interesting happens here unless we write rules encoding particular behavior, and I come to this in a minute. So we create another database, then we textualize this, normalize this a little bit, remove some noise. There's some noise related to numberings being used and so on. And then we create 2 textualized versions of those IDBs, and that's basically what we diff. And when the diff reveals that there's no difference between those representations, then DALEQ claims that those 2 class files are equivalent. So let's have a quick look back at the report. So for that particular class where DALEQ can establish equivalence, there is this so-called advanced diff report, and let's have a look into this. So everything I've mentioned a little bit earlier when I talked about that architectural drawing is actually somehow represented here at the top of this report. So there's the file locations. So for jar 1, we have the EDB. So you can actually click on this link, and then you see the relations here. So .fact files are basically comma-separated values, or actually tab-separated values. And let's see, we go to this a returns facts file. And so you can basically see facts here that correspond to bytecode instructions and the parameters some of those bytecode instructions have. So we also have IDs. Those IDs are generated during the extraction in order to identify facts. That's some of the auxiliary information that DALEQ uses during processing. So we can also see the IDBs here. So it has a very, very similar structure. It uses different file extensions. So I might change this in the future to also use .facts, but that is very much the ID. So now let's have a quick look at the rules. So if you go to the source code repository, you have to navigate down to this Java main resource folder. So at runtime, those resources are part of the DALEQ jar that's being created when you build DALEQ. And so this is a folder called rules, and it has a couple of rules. Let's first have a look at those, the core rules. And to show you this, let's just have a look at the rules for one of the most common bytecode instructions, LDC, that loads constant onto the stack. So we first declare a predicate for this here. So if your background is relational databases, that corresponds like to a schema definition, to definition of a table. And then we have a rule that basically takes an LDC fact, that is a fact that is being part of the EDB, so that's being extracted by our extraction tool. So that corresponds very, very directly to a bytecode instruction and turns it into an IDB fact. So those IDB predicates are prefixed IDB underscore, which basically has exactly the same structure, but it has this kind of strange header which encodes the ID of the derived fact, and that is how we track how those facts have been created. So that has to do with provenance. I will come back to this in a minute. We also have an additional fact here, which means it's like a guard. That is, we take a fact from this input database, from the EDB extracted from bytecode, into the IDB, where our equality reasoning is based on, unless it has been removed. So that is basically a mechanism that enables custom rules to override default behavior. So that's basically how those core rules work, and there are code generators for those. So we basically generate most of those rules from the ASM API. So let's go back to this example. Let me just close a couple of tabs here, and let's go here. Okay, so that report we have seen earlier now has some interesting differences. So it basically says there has been sorry, let me just go here. Yeah, let's start here. So there has been a particular instruction fact here where we had an invoke virtual instruction, and the way that is being computed is by means of applying a rule. So we can actually go to this rule, we can see this here. So, and what that rule basically does is it says, well, we create invoke virtual instruction from an invoke interface instruction if it is a root method. So there's some additional information here. So it's kind of logic expressed in Datalog to tell us that we infer an additional invoke virtual instructions that wasn't there in bytecode before. Right? So let me have a quick look at the rules here. So those custom rules are also defined here in our rules folder. And on top of the rule definition of this particular rule that's being applied here, we have a reference to this URL. If you open this in the browser, we can quickly do this. You find a discussion and some commits on some changes that were done to the Java compiler. And the pattern there is that if we invoke methods which are defined in the root of the Java class hierarchy, Java long object, on interfaces, then at some stage the compiler changes the strategy how to compile this. And this really explains the difference we have seen earlier. The difference can be traced back to different compilers being used in order to perform the builds. So the rules we have and applied here can then be traced. And we basically say, well, we have this additional fact here, which leads to equality. You can think about this as a normalization. And that's really underpinned by this rule, and this rule is being applied on top of those facts. And now we can actually go back to those facts. So that's our first fact highlighted here. So we basically started with invoke interface instructions. That is instruction we try to normalize. So go back here, and the second thing that goes into this is this additional fact where we define the root method. So that is basically an auxiliary predicate. The rule introduces with some facts that basically say, well, what are the root methods? The one is getClass, the other one is toString equal hashcode. So Java programmers would understand this. And based with this, we can not only, let me go back here, we can not only infer such a fact that is then be used to establish equality, we can also provide provenance for this. So we can actually display the logic that has been used in order to derive this fact. So, and that's basically how DALEQ works underneath. I maybe show you one more report DALEQ is generating here. So that can be found if you click on the little I symbol, which is standing for informative. And we can, maybe let me quickly go back here to this README. So I mentioned earlier that we have a certain processing chain that goes through constructing the initial database and applies the rules, creates a second database, and then does some normalization. We call this projection in order to create reports which are then being compared and set. Sorry, I have to find my report again. That's basically what that report is. So it's a normalized disassembly of the jar files being compared, and now we have only one such file because the comparison basically established that those transformations produce the same file. So hopefully that gave you some ideas of how DALEQ works underneath. It is really important to remember what the big picture is. The big picture is that we can make equivalence statements, but we can make equivalence statements that are backed up by provenance, that are explainable. And that is really a big thing, because if you think about this, if you have different bytecode, like what we have here, explaining non-equivalence is actually very, very simple. So you just have a diff file and you point to the differences. It's much harder to explain equivalence, because if you have equivalent bytecode, you want to have some guarantees that equivalence doesn't really mean it's something that can result in different behavior, because that would potentially mean that there are exploits or backdoors in bytecode which are different behavior, which this analysis would miss. And we basically crafted DALEQ so that is not the case, and that the decisions it makes are communicated to the engineer and can be assessed by the engineer, and therefore engineers can develop trust on the tool and the declarative logic the tool uses underneath. Yeah, so that was part 2. If you have questions, please email me, or you can also open issues and communicate with us this way. And yeah, thank you for your attention.